Hi, welcome to the Calculus 3 lecture series. And we are in the unit about the vector calculus. And this is our lecture number 6. So in this lecture, we're going to talk about the green series here. Okay. And so let's go ahead and start. And let's go to our lecture notes here. All right, so before we talk about the green series here, right? So let's just do some very quick review what we did before. So when we start this units, we talk about the line integrals, right? So we talk about the line integrals here. So you will see where we are coming from here, right? So we talk about the line integrals. We talk about is over the scalar field or vector field. So for the vector fields here, right? So the way we do that is we say, if you have the here, so you have like a f of x, y. So this is a vector field. And then we have our, we have our and the route here, right? So, or the paths here, right? So we talk about the line integrals here. So we said one way we can do that. So what is the way we can parameterize it? Okay, so that means we, we send the, we parameterize your variable x, right? So you said x is a function of the t and y is a function of the t. So basically you change all your, so if this you integrate over c's, right? So you change this path to a one single variable. So of course, the t is from a to b, right? So basically you change that. So this is from a to b. Then here, this will be what? xt and yt, right? Then you dot product r prime t's dt's here, right? So you change the whole thing into a single variables t, and you can integrate that. Then we also talk about, so like during the, we also talk about the conservative and we also talk about the conservative. So we also talk about the conservative field and, if a field is a conservative, right? So we talk about this ones here, like f of x, y. And if you can write these ones here, so the f of x, y. So if we say this fields here, if this is the field, it's the gradient field. So it's the gradient field of a real value function, f of x, y. That means that if you can write here, the f of x, y is here. This is the gradient field of f of x, y, right? So that means this is like the f of x, the f of the y. If you do that, then we can say the f of x, y is a conservative field, right? So we say this is what we call this the conservative field. Right, so we say this is a conservative field. If this is a conservative field, then we have several good properties to do that. Also, one way is here, we can test this is a conservative field, is x, y. So if this is like, if you can put this is a function like the p, x, y, this is your I components plus the q, x, y. This is your j components here. Then the way we check it, the conservative field, we say the rho q, rho x, if equal to the rho p, rho y, see here, right? And then we say the f of x, y is a conservative. Okay, so the one of the, the one of the very important characters about the conservative field is that we call this the path independent. That means if you integrate, so if you have a path starting here, if this is your first path, this is C1, right? So if your C2 is go like this way, C2, or if here you go like this way, it's C3. As long as they are, if they are in the conservative fields here, then you know that when you integrate the C1, this field, the dr, will be equal to the C2, the f of the dr, and it will be equal to the C3, the f of the dr, right? That's what is we saw is one of the very important things for the path independent, you know, if and only if, right? So we say if and only if f is what conservative, okay? So this is a very, very important here, right? So it's very convenient to use also. Then also we talk about the fundamental theory of the line integrals here. That means if it's a conservative here, right? So then if you try to integrate the f of the drs here, right? Because the f is the gradient function. So if you can find real value functions, then this ones here will just be the f of what? F of the xy. Then you put your initial point is the RA and RB, right? So it's similar like we did in the calculus truth here. Then we know if it's a conservative fields, right? So also is F is a conservative field. And then, right? So if F is a conservative field, and then for closed path, that means if this is your C's here, right? So if this is a C, you start at this point and then you end the point here. So if C is your path, then we know this one's here, the F dot dr will be equal to what? It's zeros, right? Because this is a closed path, then when you try to find this real value function f of xy, and then the beginning point, the starting point is equal to the ending point. So that's why it's 0. Okay, so now for the green series, okay, so this is all good, right? So this is all very, very good properties, you know, under your f of xy is a conservative field. And now for the green series here, we are going to deal with is how about if your field is not conservative. See here, now how do we do that? Okay, so in order to do that, so the first thing is we want to do add one notation here. Okay, so we said if C is the path, right? Okay, so C is the path, and also C is a simple closed curve. Okay, that means we talk about it. That means the C is a simple closed curve. This is C. That means the C is not going to intersect themselves, right? So like we know this type of path is not C's here, right? So now we defined, right? So we defined, okay. So we defined C is a positive orientation. So you will say it's a positive orientation. That means if the traversal TAV, the traversal of the C from RA to RB, right, is counterclockwise. All right, and then so like of course then the C is a negative orientation if we travel clockwise. So right here, so it's very similar like we defined our angles, right? So like if it's a counterclockwise, then it's a positive orientation. Of course, then in here you can say if I say it's negative orientation. Okay, so if negative orientation, that means you travel, this path goes through is what is clockwise, right? So we're going to introduce a new notations here. That means this notation is here. Okay, so that means I'm going to integrating, and then I'm going to integrating, this is a C. That means I'm integrating the C in the positive orientations, right? and of this field and under this passes here. Okay, so this is what the we're going to use this new notation for the green theory, because for the green theory, they the so like if you do the counterclockwise and the clockwise, they will yield different results here. Okay, so now let's take a look here, right? So what is green theory? This is kind of like the basic definitions here, all right? So let's take a look here. All right, so green theory is here, all right? So let's start to mark some key points here. So we say C is a piecewise curve, all right? Simple closed curve, okay? So this is my C, is a simple closed curve, and with a positive orientations here. See, you see here, right? So the, this one is go this way, this way, this way, the arrows here, right? Okay, so then this one is a closed curve, and the regions here is D. Now with that, the vector field is Pxy is the I components, Qxy is J components, and then Px and Qx are the continuous partial derivative. So partial derivative, right? So like now in here we say, I'm going to take the integration of this. So it's a Px. So basically, I'm trying to take the integrations of this this vector field over this passes here. So of course, as you can see here, right? So if f of x, y, this vector field is conservative, so then this is closed, so it will be 0. So obviously, it's not a conservative. So that's why I say, okay, so what is this integration going to be? It's going to be rho q minus rho x, rho q over rho x minus rho p rho over rho y, right? Because here, this one is not equal to 0. So we know if equal to 0, it's a conservative, right? So this is not equal to 0. So it's basically it's a drop to the R2 and integrations over what? Over these D areas here. So that's why, so the green series say, if you are integrating over this field, okay, and then it will be equal to, you kind of finding, you are integrating over these areas here, all right? So you are integrating over this area. That's why I say it's dA here. So as you can see here, right? So we know this is one of the things we checking for the conservatives, right? So if this is a conservative, then rho q over rho x minus rho p over rho y will be equal to 0. Then the whole integration will be equal to 0 here, okay? Okay, so the one thing here we need to kind of, let's take a look here, right? So in the Calc 2, so when we say we integrating like AB, f of x dx, right? So we kind of, so this one's here is basically, like if in the calculus 2, we know if this is your f of x, this is a and b's, right? Right, so this is a and b's here. So based on the fundamental theory of the calculus, we say, what is this one's here? We say this is f of, let's put it this way, so maybe it's better. So if this is f prime a, okay, then based on the fundamental theory of the calculus, so we know this is f of the b minus f of the a here, okay? So now in here, so that's my here, in R2, right? So you only use what? You only use those boundary, right? FB minus f of a. So this is FB minus f of a, right? So you only use this boundary value of the integration region. So we said green series, right? So green series looks here, right? So we say it's a kind of it's very similar. We call this the two-dimensional. So we call this is a two-dimensional, okay, the versions of the fundamental theory of calculus. Okay, so look here, right? So see here, right? So this is kind of like what? It's kind of like the similar, like I say, it's kind of like the versions of that, right? So this one's here, right? So this is kind of a similar like f prime x compared to the x, right? And then also, right? So in here, like in here, let's say you integrated over the boundary of this interval is b and a. So right now, what I'm integrating here, I'm integrating along this boundary also, right? This curve also, right? So that's why we say it's a kind of a similar, like this is two-dimensional version of the fundamental theory of the calculus, right? So because you are kind of integrating this one, this is kind of like your f prime x, and then you use the boundary. What is it? You're integrating over these, right? So, but then what is these here is used bounded by what? Bounded by the curve C here. All right. Okay, now let's take a look at some of the practice problems about the green series. Okay, so we said that f of the vector field is equal to xy squared I to x squared y, and the D is the region given with the simple closed boundary C composed of y equal to x squared. We call this C1, and the line equal to y equals C, we call this C2. Okay, so first let's try to draw our, okay, so let's try to draw our curves, right? So y equal to x squared. So let's put a little bit big here. So this is 1, 1. Y equal to x squared. So it's a quadratic, right? So it's like this one here. So this is my curves here, right? Okay, so this is y equal to x squared. It's quadratic. Then this is my C1 here, right? Okay, so now my C2 here is y equal to x. So it's a what? It's a straight lines, right? So this is y equal to x. So let's say that I'm combining with these two curves with a positive orientations. So that means I'm starting here, right? So here, this go here, this direction, and go down here, right? So I have two curves here. So I'm going to evaluate, right? So I'm going to evaluate the f of the dr. So in here, because of this notations here, they tell you that I'm going to the positive orientation. That means counterclockwise, all right? And now in here, so it's f of dr. So let's say use the two methods here. Like we first start this unit, we said the vector integration, you can always use parametric, right? You can parametricize your x and y's here. All right, so let's see here. Let's first try our, the green series here, right? Because we just learned that, right? So let's see here. So the green series, so this is pxy, this is qxy here, right? Okay, so this is pxy, this is qxy. See here, let's try to our green series here, okay? So because, so this is the first ones here, let's try green series, okay? So after we try the green series, okay, so for green series here, so I know I'm doing the CFDR. That means really is the C1 FDR plus C2 FDR, right? Because I have two different curves here, okay? And so okay, so okay, so for the green series here, okay, sorry, I gotta mix, I try to parameterize that first. Let's try the green series here because we put here is a green series. Okay, so the green series tell us rho Q, rho P, rho Y, right? So, okay, so let's do rho P, rho Y. So the rho P, rho Y is 2xy, then rho Q, rho X is what? Is 4xy, correct? Okay, so now the green theory tell us if I'm doing the C FDR, what I'm going to have a double integrations over this area, then the 2xy minus the rho q rho x, right? So it's, we said this one is here is rho q rho x minus rho p rho y over this area, okay? So that means I'm over this D area. So rho q rho x is 4xy. So this is a 4xy minus 2xy dA. So what is here? So this is this is 2xy here, right? Okay, so this is 2xy. Okay, so now it's in dAs, right? So this is my areas here. Did you see here? This is back to, you know, so this is back to what is the calculus 2 here. So we are integrating over these areas here. So now I can do it. So I will say, okay, so this is will become very easy. So this is a 2xy. Then you can say, hey, I want to integrate dy first. Then dx, right? It's become to what we learned in the Calc 2, how to do the how to find the integration in the region. Okay, so if you do, okay, so if you, let me get a better, okay, here. So that means dy, that means you integrate these directions, right? You integrate this direction. So where it start x squared, right? So that's what you put here. This is x squared. Then where you end here, you end at x. Then afterward, you integrate out x. So what is the x here? From 0 to 1 here. You see here, it's simplified a lot, right? So now I think everybody will be able to do this simple integration. And the answer is 1 over 12 here. Okay, so this is green series, awfully pretty easy here, right? So, but also like when we start, we say, hey, we can always do a parametrics, right? Okay, let's parametric ones here. We can always use our basic line definition and try to do it. Okay, so the first one is here, we know, because you are looking for this integration C f of dr. So I need to change that to two paths. One is C1 f of dr, right? Plus C2 f of what? dr, all right? So the C1 is here, right? So I, because I have two passes here, right? So C1 is here. C1 is this one, right? So C1 is y equal to the x squared. Okay, so C1, that's parametrize it. I said C1 equal to x squared, so I can have x equal to what? I can have, okay, so I will parametrize my C1s here. So it's, if I let x equal to t, so what is my y? Y will be what? T squares, right? And then we know that then we said the t in here is from 0 to 1. Then here you have dx, so this will be equal to what? Dt. dy will be equal to what? 2t dt. All right. Okay, so now let's substitute to the first ones here, the C1, right? This will substitute C1s here. So this is a C1 f dot dr is going to be equal to the C1, my pxy. The pxy is xy squared dx, right? Plus qxy is 2x squared y dy, see here, all right? So now let's plug in here. See here, the t is from 0 to 1. Now, in here, right, take a look here. The x here is t, y is t squared. So you need to replace here with t. Okay, so the first one's here is what you have here. So you have t times y squared. So you will have x is t times t square, the squares, right? Then what is dx here? Dx is what? Is dt. So it's 1, right? Okay, so it's 1. Then plus 2x squared. So it's 2 times t squared times y times what? Times t squared. dy dt is here, right? So the dy dt is what you have. You have another t dt, right? Another t is here. And then overall, right? So now the overall is here. You change it to what? You change it to dt's here. So you change all the trace of C1 to the what? To the t. Now, if you combine it a little bit, and so you will combine this, simplify this, and this one will give you 0, 1. So if you combine it, it will be 5t fifths dt. Okay, so the answer for the C1 here is 5/6. So that means this is the 5/6 or the C1 pass. Okay, so now we have a C2 passes here, right? So the DR, the C2 passes here. So now that's the same way. Let's try to parametrize it, right? So this one's here, is a line y equal to x here. So initially, you will say, hey, I can let x equal to t, y equal to t also. But in here, look at the orientations, right? So this line y equal to x here, you are going this directions, right? Okay, so you are going from 1, 1 to 0, 0, right? Okay, so now I can parameterize x equal to the 1 minus t and the y equal to the 1 minus t here. Then we have a t is greater than 0 and less than 1. See here, if you put a t equal to 0, you get 1, 1, correct? If you put a t equal to 1, you get 0, 0. So it's because go this one. That's how do you parameterize this one here. So the same way, the dx equal to the negative dt, dy equal to the negative what? dt here. Okay, so now let's take a look at my C2, f of the dr. Okay, so this is from 0 to 1. Then you still do the same. You plug back in, right? So 1 minus t. So it's x. So it's 1 minus t times 1 minus t to the what? To the seconds, right? And then times the dx dt is negative 1. Then plus the 2x squared. So it's 2 times 1 minus t to the square. Then 1 minus t. All right. And then the dy dt is here is negative 1. See here, you change everything to t. See here. Okay. And now if I combine this a little bit, I will get this is 0, 1. This is will be negative 3, 1 minus t to the cube dt. And now your integration is 1/12. So because the whole line integrations is equal to the sum of the C1, right, plus the sum of the C2, right? So it will be what? And so hold on, this one's here. I'm sorry, this is the, I'm sorry, here. This is the integration for this one's here is will be negative 3/4. Okay, so because you are adding the F1 and the C1 and the C2s, right? So you add this one and this one. So that's what going to be 5/6 plus negative 3/4. So you will get 1/12. Hey, as you see here, hey, this one and this one. they give you the same answers here, right? So that's why the green series, so look here, it simplified a lot compared to my previous parametric slides here, right? Okay, so now let's take a look at the next examples here. Okay, then after we do the next example, we're going to stop here because we're going to introduce another new concept. And so in here, this is just like we practice the green theory. Okay, so let's say evaluate using green series. So try to do this integration. C is the triangles here. Like we talk about, you can always do the parameterize, but then sometimes, it will be pretty tedious, like this one here, like a 0, 0. This is 0, 0, 0, 1. Okay, so this is 1. So 0, 1 is here. Okay, so this is the area, so this is the triangle. I'm trying to, it's not a triangle here. So it's a triangle, but it's not the area. So let's put it here. And so here. Okay. Okay, so this is y value. This is 1. This is 1. So this is 1, 1. So let's say I'm trying to integrate this field and the path C is like this way. That means I'm integrating this one go this way, right? So this go this way, and then go this way, then travel back, right? So there's close interval like this way. So that's what is my path goes here. If you do the parameterize, you need to parameterize the 3 line segments, right? This one, that one, right? Okay, so now let's take a look, the how easy and so we can get this one done here, right? So okay, so this one's here, like, okay, so let's see here. So this is my PXY, this is my QXY here, so mark it. So this is a PXY, this is a QXY here, right? Okay, so now by the green series, let's say the rho P, rho Y is what? Rho P, rho Y is X. Rho Q, rho X. Rho Q, rho X, is 0. So, okay, so it's 0. So I know my, by the green series, you will see how it's easy to simplify that, right? So by the green series, the C, okay, then the xy dx plus y squared dy by green series, I can change to this right triangle, not this triangle here, right? So if I call this triangle is this here, that means you can do here, this here, right? And then the top here is rho q, what? Rho q minus rho p, right? So it will be 0 minus x. Then you take the integration of this area, okay? So now in here, I can just change that. So this is negative x. So you want to do this integration, you can do dy or dx first. So like if I say I want to do dy dx, that means it's the y's, right? So I'm going to this direction, do y. So what is my bound here? If I do y first, that means I'm going from here to here, right? So this is y equal to x. So it's from x to what? X to 1, right? So after I finished y, I just integrated the x together. That's what we practice a lot when we were in the calculus 2. So x is from where? 0 to 1, right? So this one's here would be very easy. Everybody should know how to do integrations for this one. So this will be equal to the 0, 1. Then this will be the x squared minus x and then dx. So finally, you will get a negative what? 1 over 6 here, okay? So look at, how easy the green theory to simplify. You know, if you don't use green theory, will you be able to find the answer? Absolutely, right? So you can go to do the parameterize, the 3 line, the 1, 2, 3. Then you combine these 3 lines, you do the integration for each line, then you add them together. So here. Okay, so now let's take a look at the same ways here, right? So this one's here. All right, so the same things here. This is my PXY. This is my QXYs, right? Okay, so now let's see here. So the PXY is here. So this is PXY. This is what? This is the QXY. Right, so the rho P rho Y is equal to what? 12xy. Okay, then rho Q rho X equal to what? Rho Q rho X. Oh boy, it's 12xy also. So you see they are each equal to each other. So we know if they are equal to each other, this is a what? This is a conservative field, right? If it's a conservative field and then I have a closed path, what is the integration going to be? Equal to 0. Okay, so then let's take a look from the green series. So this integration also can change to basically over these regions, right? Then it's rho Q rho X minus rho P. So it's 12xy minus 12xy over this region dA. So I have a D, so this is 0 dA. Oh yes, of course it's 0 also. All right. So let's kind of with another contradict with what we learned before. If it's a, if it is a conservative field, then it will be the closed loop, closed path. The integration will be what? Will be 0. So here still the same. Okay, that's it. And so let's stop at the this video here, and then for our next video, we'll talk about a little bit more and the other concepts here. All right, that's it. Okay, so nice talk to you. Okay, bye.